All right, and we're live. So, in today's lesson, we are going to consider reaction mechanisms and potential energy diagrams. This is kind of interesting because we really start to get deeper into the mechanics of how reactions work. When you think about a chemical reaction equation, it's kind of like watching the sports news at night. They don't go through the whole game step by step. They just say, okay, well, here's the score, here's the highlight reel. And so, in a way, it's kind of what a balanced equation is. It says, here's what you start with, and here's what you end with. But it doesn't show you the play-by-play on how it does that. And you might wonder, why does that matter? Well, it's really interesting because a reaction mechanism really tells us kind of the collisions, these specific molecular events that lead the reactants to turn into the products. And when we know that, it's like knowing the inner mechanism of something. You can influence it in a whole different way. Kinetics studies like this to find out the mechanism of reactions allow us to determine and develop catalysts that will make the reaction go faster. Um, it may also give us insight into ways to stop reactions we don't want to happen. So really, a lot of kinetic studies are done to unravel reaction mechanisms, try to figure out how the reaction works. And we're going to hopefully see that connection today. So let's just dive in and see what happens. There's a problem set here. It's really lengthy, so I'm not telling you to do it all. Just kind of, you might want to go through some, and we'll do some together just so I can highlight the kinds of problems that you should be able to solve, the ones that are most commonly going to be seen on an AP exam, for example. So let's start out with kind of somewhere where all of this conversation began with kinetics. We talked about something called collision theory, and we said there was three basic principles. In order for a reaction to happen, the molecules have to collide. They have to meet. And when they do collide, they have to collide with enough energy, what we call the activation energy, in order to break the existing bonds so that the new molecules or new bonds could form. And they also had to hit in the right orientation. They had to hit each other the right way, in the right direction or angle, so that the reaction could also happen. So those are the basic principles. They must collide with sufficient energy and in the correct orientation in order for the collision to successfully convert reactants to products. Now this model is pretty simplistic. It's like crash, products. Um, the reality is a little bit more complicated, and the collision theory is simple and useful, but it doesn't tell the whole story. So we're going to look at just a slight modification of this in terms of something called transition state theory. It's very similar for our purposes. The difference is, and you don't have to write all this word for word, but I am going to basically, this is a summary of everything we're going to talk about now. Instead of us imagining that there's just a collision and a conversion to products, we imagine that as the molecules approach, in the process of colliding, they go through a transition state, meaning we form something that is not the products or the reactants, called the activated complex. So instead of it being an all at once kind of process, there's a transition. It's kind of a little bit more detailed. And we're going to look at the energy profile of such a transition and see what it tells us. But for the most part, as these three molecules are approaching, we're starting to form bonds between them. And some of the bonds within them are weakening. And as this is happening, we're creating this really high energy species that is unstable. And then if everything goes right, it breaks apart into the products. And that's how the reaction goes. So really, this is just so I can tell you about the energy diagrams. So let's get into what a potential energy diagram looks like. These are questions that will come up. So for a single collision process, like let's say A crashes into A and becomes A2, like boom. On the y-axis, we can measure the potential energy, meaning basically the energy of the system throughout the reaction process. On the x-axis, sometimes they call this the reaction coordinate, but that's hard to visualize, so I'm just going to call it reaction progress. Well, sequentially, we start at some energy with the reactants. And we're going to end with the products at some other energy. My question is, what are the possibilities? In other words, could the products end up at higher energy than the reactants? Yes. Could the products end up at lower energy than the reactants? Yes. Those are both possibilities. Could they be equal? Very unlikely. So let's start with the products below. So let's say the products end here. There would be a net energy change in this direction, and we'll call that delta H, where delta H is what we've been calling the heat of reaction. The fancier word we're going to learn in another unit in class is the enthalpy, but for now heat is good enough. And we've already kind of alluded to this back in class during the equilibrium stuff. We talked about endo versus exo. What does this look like to you?
Exothermic?
Yeah. In other words, delta H is negative because we're at lower energy than we started, so the difference is a release. So this represents an exothermic process because energy is being released. But there's one piece of this graph missing that's really important to understanding kinetics. If it was not here, in other words, if this was just a direct line between these two, this reaction would be essentially instantaneous at all temperatures. It would just happen right away. Here's why it doesn't. As the reaction is happening, and this is where the transition state theory comes into play, there's initially an increase in the energy of the system as the molecules approach each other, and they hit a peak. And from this peak, as the new bonds start to form, we get the energy changes that eventually lead us to the products. So what I want you to notice is that if we kind of put a dotted line here, this difference between the products and the reactants hasn't changed. What's changed is we added this energy hill. This hill is what we call the activation energy. And why this is interesting is because think about this. You all know that paper is flammable. You know that your clothing and your hair is flammable. And you know that for them to burn, they need to react with oxygen. So here you are sitting in a room filled with oxygen, and you're not burning. Why? Aren't the oxygen molecules bouncing off you all the time? What's going on here? Well, this activation energy is kind of like a barrier to the reaction happening. It's kind of preventative in a way. In other words, the oxygen molecules crashing into you are just not hitting hard enough. They're like going boink, 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 boink. They're not moving fast enough to collide with enough force to initiate the reaction. Thus, all the papers and things that are flammable in your room aren't on fire. But you know that if you take a match and put it to a sheet of paper, that gives a large number of molecules the necessary energy to overcome this barrier. And the reaction goes a lot faster, and then it engulfs in flames, right? So think about a graph we saw a long time ago called a Maxwell-Boltzmann distribution, where here we had like the number of molecules, and here we had the kinetic energy, for example. So imagine now at a given temperature, at a low temperature, the majority of molecules, we said, are somewhere near the peak in energy. But what if the activation energy is somewhere over here for the reaction? Activation energy, whatever. Actually, let me abbreviate it the way you're probably more likely to see it, which is E subscript A. So if this is the energy we need for the reaction to happen, only the molecules here and later are going to react. In other words, very few. I can show you this. Did you ever see a document, a really old paper document, and how it looks? Kind of yellowing and kind of, right? That's basically because it's burning in slow motion. Because only a tiny fraction of room temperature oxygen molecules have enough activation energy to react. Just little by little, the paper is reacting. If you waited thousands of years, that paper will eventually turn into ashes as if you had burned it all at once. Because it's just taking time. But we can speed it up, and we've talked about how kinetics, right, how we affect reaction rates with temperature, by heating up the system. So if we heat up the molecules, we know that this shifts. Let's exaggerate it a little bit. So now the majority of molecules are here, but look at how many more now are at or beyond the activation energy threshold. We've given a lot more molecules at the higher temperature the energy to overcome this barrier. So one of the reasons why heat speeds up a reaction is because it increases the fraction of molecules that have the activation energy so that the reaction collisions are successful. But there's another way that we can speed up a reaction other than heating it. Yes, concentration. But what can we add to a reaction that makes it go faster just by adding it?
Catalyst.
Yes. Here's a cool thing about what a catalyst does in this context. What a catalyst does, instead of making more molecules have the energy to get over the hill, it lowers the hill. So catalysts, one way that they work is they provide an alternative reaction collision sequence. And so I'm going to write a blue line in here, and I'm going to label the blue line with catalyst. So even if I stay at the same temperature as before, a lot more molecules are going to be able to react successfully with the catalyst because now we've made the reaction easier. So I want to make sure you understand this difference. From the energy profile point of view, raising the temperature makes more molecules able to climb the hill. Lowering the hill makes it easier for the molecules to get over it. Two different mechanisms, but both lead to speeding up the reaction, and we're looking at that from the point of view of energy. Now, what if we did some comparisons between these types of charts? So the first obvious comparison is exo versus endo. If we were looking at a single collision, again, so again, we're going to see that mechanisms are often more complex than just one crash. There's often a sequence. But let's just consider again a single collision in the endo sense. We still start with the reactants at some arbitrary energy. We still go up to some activation energy, but when we come back down, we stop higher than we started. Here's the reactants. Here's the products. The peak is what we've been calling the activated complex, the weird structure in between. And now, when we want to define all the energy aspects of this differential between reactants and products is going up. Therefore, there's an increase. That's what makes it an endothermic reaction overall. But notice that our activation energy is going to be measured from baseline of reactants to the peak of the activated complex, the peak of the hill. So our activation energy is here now. Okay? Now watch an interesting thing. Remember how we said the temperature helps and drives the endothermic reaction better than the exothermic reaction? Watch how easy that is to prove now. If you look at the forward reaction of this picture, it's endothermic, and the activation energy is this whole giant leap. It takes a lot of energy. But what if we ran the reaction backwards? Now the activation energy would only be this. So it's not as hard to go backwards here from the energy point of view. So raising the temperature is not really helping me as much backwards as it is forwards. In other words, the endothermic reaction needs more help. So when I'm raising the temperature, what I'm effectively doing is proportionately really helping that one more than I'm helping the exothermic version. And so that kind of now ties to what we said when we looked at the equilibrium shifts in terms of temperature. Um, does that make sense so far? Or I should say, do you have any questions so far?
Can I ask a question?
Yeah.
So you're saying because when you heat it up, it would help the endo because there's more of like a potential for it to help. Like it'll help more get up the hill, but the other way around, there isn't much of a hill to get up, so it wouldn't make a difference.
Comparatively, right.
Okay.
It's like saying, let's look at the government stimulus. They're sending everybody, what, like a $600 check. That helps everybody. But does it help the millionaires as much as it helps the people who are poor? Right? $600 to the millionaire isn't going to make much difference. Yeah, I can buy a few more Big Macs or whatever. But $600 to somebody who doesn't have anything to eat or can't pay their rent is going to be a huge difference, you know? And that's kind of the same idea. Um, the other thing that's interesting to compare is what if we had two energy profiles, and I just wanted to ask you one simple question. So let's say the first one looks like this, and the second one looks like this. Just comparing these side by side, which of these represents, in your mind, the faster reaction at the same temperature? Which one of these would you think go faster at the same temperature?
Second one,
Why?
because there's a lower hill to go over.
Exactly. And so what we see is that this activation energy barrier is paramount to understanding kinetics. It really is a big part of why, or what, I should say, controls how fast a reaction can go, and why temperature influences reaction rate, and why catalysts influence reaction rate. Obviously, this doesn't show the concentration effect, but the concentration effect we understand pretty easily. The higher the concentration, the more collisions we get. The more collisions, the more chances there are for reaction. This really speaks to what fraction of those collisions are going to be successful. Because as we've just said, we're sitting in a room full of oxygen being collided with it all the time, but the vast majority, luckily, of those collisions with our bodies are ineffective because they're just not energetic enough. And so we're not all screaming in pain on fire. Yay. Okay, so that's kind of phase one. But again, a reaction mechanisms are not very interesting when it's a single collision. Whack. Just like a baseball game would be pretty boring if it went like this. Okay? There's a big build-up. Everybody lines up on the field. Batter comes in. One pitch is thrown. One swing is swung. And it's up. That's it. Game over. Who won? That wouldn't be a very interesting game. A baseball game is a series of many collisions and many happenings that adds up to a final result. It's true of almost every chemical reaction that there's a sequence of steps that lead us from reactants to products. That's where it gets interesting. And what's really cool is we can draw a connection between those series of steps and the rate laws that we've already studied. In fact, the whole point much of the time of finding out the rate law of a reaction is to see if our mechanism is right or wrong. We can actually assess the molecular collisions and if our theory makes sense based on the actual experimental kinetics of the reaction. And that's what I'm hoping to kind of clarify with you today. So let's see what that looks like. The next thing we have to consider here is something called molecularity. So let me scroll down to that segment. So this is going to start to really blur the line between what we've been doing in kinetics and what we've been doing in equilibrium. Remember how I said you cannot assume the order of a reaction by the coefficients? Remember we had to do those experiments with the data, like keep this one constant, and if this one doubles and the rate doubles, it's first order and all that stuff? Well, it turns out for an elementary reaction, meaning a single collisional step, the coefficients are the orders. What? You just said we couldn't assume. This is different. When I write a chemical equation, I can't necessarily assume it's an elementary single collision step. If I know it is, then it's going to follow the rules you see on the screen. So let me kind of go through them and explain what's going on here. So if I have a single molecule that just breaks, that's called a unimolecular reaction, meaning only one molecule is involved in the process. It should make sense that that's a first order rate law, because if I have a million of these molecules and they're breaking at a certain rate, it should stand to reason that if I had 2 million, they're going to break at twice the rate because there's twice as many, right? Because there's really nothing else going on. So what you'll notice then is I can write the rate law directly for an elementary step using the coefficients. Here we are allowed to do that. But again, how are you going to know when you're allowed and when you're not? If the problem is talking about mechanisms where there's a sequence of steps, that's when you're going to be able to do this, and you're going to see that as I do my examples. But let's continue talking about what are the possible elementary steps in a reaction. The next type of elementary reaction is bimolecular, meaning two molecules have to crash. It can be two of the same molecules in this case, or it can be two different molecules. But both of these are second order reactions. Look at what's going on here. Here, we can write the rate law as K times the reactant raised to the power of the coefficient, where A plus A just means 2A, obviously. Here, it's A and B both to the first power, but we said the overall order is the sum of the orders. And so this is, again, a second order overall rate law. But you'll notice I'm able to write a rate law not as in terms of X and Y. I can directly use the coefficients in these cases. These term molecular is about as far as you can go in an elementary process. Let's think about why this is logical. Think about what and I do this as a demo in class when we're in class. If I say throw a ball up in the air and catch it, that's like a unimolecular. I mean, that's easy as heck. But I give my class 10 extra credit points if they can do a simple thing. I give each side of the room, like one kid on one side, a tennis ball. And all they have to do is throw them in the air and make them hit in the air. It's not easy. You have to aim just right and get them to hit at the same point at the same time, two different things. And usually they get that. And then I let them play for double jeopardy. I say, all right, now let's try a term molecular reaction. Now I give a third kid a tennis ball. Now all three people have to throw it in such a way that all three balls hit at the same time in the air. And they'll sit there for the next 3 years and never get it. It's really just hard to do that. So you can imagine in the molecular world, it's also really hard. Yeah, there are some reactions that are term molecular in an elementary 3-in-1 collision, but they're very rare. So most of our mechanisms are going to be combinations of unit and bimolecular simple reactions that add up to the overall process. And that's what I'm going to start showing you now. How does that look and what can we interpret from it? So are there any questions about what I mean by an elementary step here and how we're allowed to use the coefficients in writing the rate law?
Can you keep this slide up for like a minute?
Of course. I'm going to make it look like I'm frozen on the video, so if somebody's watching, except my eyes are moving. That didn't work. Okay. Krista, you good or you still need some time?
I'm good now.
Okay. So all I'm going to do next is I'm going to take an actual mechanism and kind of reverse engineer it so you can see how all the parts fit and what it means. This is the key slide that is going to really tell us all the main ideas about what mechanisms tell us about reactions. So I'm going to define each of these terms that are important and show how they fit into this mechanism. So this is considered a reaction mechanism, meaning These are elementary steps, and I'll number them for our purposes, 1, 2, and 3. So this is saying 3 different collisions happen to convert the original reactants to the original products. But I'm not even showing you at this point what the overall reaction is. We're going to find it in a moment. Now the first thing it asks us for is, what are the intermediates? What does that even mean? Let's define it. An intermediate is a temporary molecule that forms in one step, but then is consumed in a later step. And what that means is it's not part of the overall reaction. It's transient. It's formed in part of the process, but then consumed. So it's kind of a stepping stone on our way to the final products. All right, so let's make that note. It's not in the final reaction equation. Sorry, I'm squeezing a lot of detail in here. It's not going to end up in the final reaction equation. Now, just from that definition alone, can you look at this sequence of 3 reaction steps and tell me anything you think fits that definition?
HOCl.
Okay, it was produced here, but it was consumed in the very next step, right? It becomes a reactant here. So we made it first, but then consumed it later. And so now I'm going to cross it off because it cancels out, right? It's on both sides. So when it asks for identify them, I'll just list them here. So Hockel fits this definition. Anything else that fits the definition that you can see?
HOBR.
Hober. Hober fits the definition. It's produced in step 2, but consumed in step 3. Hober is an intermediate in this case. Anything else?
Would OH be one?
Oh, yes. Even though they're not directly one step after the other, it doesn't matter. I said any subsequent step. So it's produced in step 1, but then consumed in step 3. So hydroxide is also an intermediate. Now there's one that looks like it kind of works, but it doesn't. Do you know which one I'm referring to?
Water.
Yeah. Why does water not fit this definition?
Because it wasn't created in the first step.
It was already
Like,
there, right? It was already present from the beginning. What does that mean? Ah, wait a second. So I have to erase the definitions in this space as I go because I run out of room. That's all right. You can always review the video if you have to. So now when we look at what a catalyst is, a catalyst in this context is something that you put in the reaction, so it's already there. And this type of catalyst, which is called a homogeneous catalyst, it gets, I'll say, into the reaction, but then it comes back out unchanged. Meaning it might get changed during the course of the reaction, but it gets regenerated. So overall, it doesn't get used up. That's exactly what we see happening with the water here. We're starting with water, and it's obviously reacting, changing, but it's coming back as water. That's a catalyst. So in this case, water was a catalyst. Yes, water can be a catalyst. Now, the next thing we're being asked is to write the overall reaction. How does that look? So like a lot of the problems we've done this year where we're combining multiple equations, we're going to add them like algebraic expressions. We're just going to cancel things that cancel and write what's left over. So in the end, the overall reaction that we were describing is really just a single replacement reaction in which bromine knocks chlorine out of a molecule to form a different molecule. I mean, this is the overall reaction. So this sequence of 3 steps is a mechanism that could explain in the presence of water how each collision happens. Notice these are all bimolecular collisions, just 2 molecules colliding here, 2 colliding here, 2 colliding here. But it explains how it happens. And just one more point. If there's a catalyst, we write it over the arrow. So that's why the water ends up here, and we know it's a catalyst, not an intermediate. You'll notice none of the intermediates are in this final equation. Here's what's really interesting. Here's where it really gets interesting. You'll notice I labeled the relative rates of the reactions. Why? What does it mean? If I have a chain reaction, if I have a sequence of reactions, what's going to control how fast the whole system can run?
Activation energy.
Let's be more generic than that. You're right. In a very specific way, you're right.
The slowest one?
Yeah. No matter how fast the second or third reaction go, don't they have to wait for the first one to crank out its part? Like if you're doing a sequential system of, like a job where, let's say you're sending out mailers, you know, one of you is putting the stamp on the envelope, one of you is writing out the address, one of you is stuffing it, one of you is closing it. Whoever goes the slowest in that chain of events controls everything because everybody has to wait for them, right? In the same way, the slow step answers question 4. It's always the rate determining step, meaning that the rate law is really going to depend on this step because the fast steps just crank right out as soon as the slow one is done. And it doesn't always have to be the first one. I'm just pointing out wherever the slow step is, that's where really the kinetics is going to be affected. All the fast steps are just not really consequential to the speed of the overall reaction. So in this case, our answer was step number 1. Now this last thing about sketching the potential energy diagram is actually really interesting too. I know I keep saying everything's interesting, but that's because I'm interested in everything. I'm going to do my best to sketch this, and so far the only potential energy diagrams we saw were single collision. So there's only one activation energy, one peak, as it were, one hump. But we're not talking about one reaction anymore, really. We're talking about a sequence of 3 reactions. Every single collision, every single elementary step is going to have a hump. It's going to have a transition state and an activation energy. So I'm going to do a sketch and try to justify it for you. And I'm going to do it kind of small here because I'm tight on space. But because there's 3 steps, I expect there to be 3 humps. Now, the problem is I don't have information here about endo and exo for each one, so I'm just going to make some assumptions for our purposes. So this first reaction is slow. We start with the original reactants, and I expect since it's slow, it's going to have a pretty steep activation energy. What I don't know is if it's endo or exo. Let's just pretend we think it's endo, whatever. So let's say it stops somewhere here, and that's step 1. The second reaction and the third are fast, so they're going to have a lower activation energy. Let's pretend that one's exo. And then the third, again, let's pretend it's exo. And let's put our products down here, and we've just made the assumption that the overall reaction is also exothermic. Again, the exo-endo part, we don't have enough information to be sure. The main characteristics I want you to notice is that each reaction has an activation energy. There's 3 humps in this process. There's still an overall enthalpy change between the reactants, which are these, and the product. So when I say delta H for the overall reaction, I'm referring to just the net change. But each sequence of collision has its own activation energy. And you can see that the one with the highest activation energy is the rate determining step. It's the slowest one because it's the hardest one. So this is just so you can tie in your mind when there's a multi-step sequence mechanism, the potential energy diagram is going to have also multiple humps. And that's really the main thing I wanted to connect here. So that's all this was really asking us to do. And we did, in fact, assume it was exothermic correctly because we were told to overall. So could it be stuck at some point in the middle? It could be slower in the middle, but I wouldn't say stuck. That's an interesting way to think of it. Some of the collisions are stuck in the sense that a specific collision in a specific instance may not happen. So remember, all of this is still controlled by the fact that zillions of molecules are doing this at the same time, and that some of them are getting over the humps and getting to the products, but some of them are not. And that's why it doesn't all react at once. That's why the reaction takes time. Because as the molecules are colliding, sometimes they're successfully getting through all the collisions to the end, sometimes they're not. So some individual collisions, I guess, get stuck, but the overall process can keep going. So this gives us at least the initial defining characteristics of what a mechanism kind of looks like. The next thing I want to do is show you that we can now tie a mechanism to a rate law. This is the part that it really gets interesting. Oh, there I go again. Okay. Let's see. We'll start with an easy one. So what we're now going to look at is using, let me write this in your notes because it doesn't really have a title for this. We're going to use, or say deduce, a rate law from a mechanism. And here's the thing. When we write a mechanism, we don't know if we're right. We have to have some experimental evidence to verify it or rule it out. And so this is one thing that one area of chemistry people, this is their focus, is they're literally trying to figure out what's the right mechanism for reaction. So let's do that, like I said, in a simple case first, and then we'll look at some that are a little more complicated. So I'm going to take a look at this one here. Let me take all of this over. Okay, I'll just copy it like this, I guess, whatever. Because I just don't have enough room to write here. What's it going to give me first? Okay, well, that was nice. I'm getting rid of the title now. Sorry. Always drama. Always drama. Okay, and we'll take this over. Okay, so here we have two elementary steps. And we want to look at what's the overall reaction, find any intermediates or catalysts, and then deduce the rate law for the proposed mechanism. Here's how it goes. The overall reaction, I think we've kind of figured out pretty easily. Let's see what cancels out. Well, we can eliminate one of these on each side, but not both. We can eliminate, it looks like this on each side. And overall, then, it seems to me that NO2 reacts with CO to produce carbon dioxide and nitrogen monoxide, right? I don't see any catalysts here because NO2 is a reactant. I know we started with it and saw some come back in one step, but overall it's still a reactant, so it's not a catalyst. Now, once we've come to that conclusion, we can also identify our intermediates. I would say NO3 for sure is an intermediate, so there's no catalyst. And I believe that's it, right? I don't see any other intermediates. Now deduce the rate, that should say rate law, sorry, that is consistent with the proposed mechanism. How do we do this? Well, which of these are the rate determining step again?
The slower one.
Thank you. So the rate determining step is the slow one. So we're going to take this and write a rate law for it. What would it look like? Right here. So if we take the rate law for this, we would do rate equals some constant k, NO2 times NO2, right, to the first power, so it would be squared. So this is the theoretical rate law that's predicted by the rate mechanism here. If this is the experimental rate law, like in other words, if we did an experiment like the kind we talked about at the beginning of this unit, and we got the same rate law, we'd say, yeah, this is consistent with the mechanism we're proposing. This mechanism predicts a rate law that matches the one in the experiment. So our mechanism looks good. But wait a minute. What if we found out, and do you remember how we were originally writing rate laws? We wrote them in terms of unknowns, right? So if this is the overall reaction, we call this like X, and we call this Y, and we did our experiments. What if we found out that this reaction, whoops, experimentally now, so let's focus on as if this were experimental. What if we found out it was first order in both of these? Would this mechanism work? Would this mechanism be consistent with this rate law? No. Because if this were the rate law, this is saying the rate depends on the carbon monoxide concentration. This is saying it does not. This mechanism predicts a rate law that says that CO has no effect on the rate. If our experiment shows that it does, then we know something's wrong with our steps. Now, you don't have to learn how to propose rate laws. That's way beyond the scope of our course. But you should be able to compare by what we're showing you whether or not a mechanism fits a rate law that's known, and at least rule it in or rule it out. So this rate law implies that we'd have a different mechanism going on versus this mechanism predicts this rate law because the slow step written according to the rules we've learned gives us this expression. That's the essence of it. Let me pause and see if you have any questions. Anything? Well, to put it another way, if we did the whole experimental of data tables to show what these orders were, we would have found, if this was the correct mechanism, that X would have been 2 and Y would have been 0. That's what our experiment would have showed. And then we would have said, okay, so the rate law is K NO squared, sorry, NO2 squared. And therefore, this mechanism explains it. This mechanism is consistent, at least, with the rate law that we measure. I think you're going to need to see a few more of these before you get the hang of it, so let's look at another one. Sometimes it's impossible to even ask a question or know if you have a question until you see another one and think about it and see what you can do. So let's pluck another one out of the notes. Ugh, wrong thing. And see what that brings up. So let's try it, whoopsie, with this slide here. So let's go down through the whole process. This is a pretty simplistic one. And it brings in another kind of pseudo skill that you need to understand to apply here. And in our case, it actually is easier because we've learned about equilibrium already. So I can kind of take advantage of that. So first of all, the rate determining step is obviously very simple. It's always the slow one. So in our case, it's step 2. Which species are unstable intermediates? Things that are produced and then used up. So the monatomic oxygen. Again, if you're not sure where I'm getting these answers, just say something. Which species is a catalyst? Well, just based on the way it's written, the argon seems to be acting in some form of catalytic way. So we'll just say the argon. It's not getting directly into the reaction, but there are such things as heterogeneous catalysts and other mechanisms of catalysis. If there's time, we can talk about them later or next time. But I don't want to do too much in one day because it's already been a long day, right? Okay. Now, let me skip to number 5 for a moment where it says just give me the overall reaction. To do that, we cancel our intermediates and just combine the terms of the two equations. So we'd get 2O3 producing 3O2. 203 makes 302, right? Just adding the two equations and canceling where we can. Now this is the trickiest part. The best overall rate law that is consistent with this mechanism. The first thing you have to understand is we look at the slow step because that controls the rate. This initially we're not going to care about. We just have to look here. So if we follow the rules that we saw in the last example, we're going to write a simple rate law based on the reactants raised to their coefficients. And we go, there we go, I'm done. This is wrong. And here's why. This is an important note. A rate law cannot contain intermediates because they're kind of not really there. They come and go. So you can't really have it in the rate law itself. And that means there has to be some way we can substitute it out. So we're going to have to use some kind of mathematical substitution. How is that going to work? Well, lucky for us, we have a second step that we can take advantage of. And it's an equilibrium step, meaning it's really two reactions. Check this out. This is pretty neat. So if I rewrite this equation, it's really two reactions, right? It's saying that the ozone is becoming these two parts, and we could call that the forward reaction. But it's also saying these two pieces can react back to form the ozone, and that's the reverse reaction. And what did we study about equilibrium? We studied that the rates are equal forward and backwards. Now check this out. If we write the forward rate law, we could say, well, the rate in the forward direction would be based on some forward rate constant times ozone to the first power. But can't we also write a rate law for the reverse reaction? Oops, there's a question or something here. Oh, no problem, right? All right. In the reverse case, we'd have a new constant, call it the reverse rate constant, and we'd have O2 to the first and O to the first. And the key point here is because this is an equilibrium, these rates are equal. So we can say the forward rate law is equal to the reverse, whoops, the reverse rate, oh my gosh. The forward rate law is equal to the reverse one. And again, I'm really just doing some algebra here more than anything else, if you really think about it. Wow, this is getting harder and harder to write on. Fail. But now, notice that I need to substitute something for this oxygen, right? So if I solve this little system for the oxygen, what would I do? I would take this constant times the O3. I would divide this constant, and I would divide the O2. So now I have this big pile of junk that I can set equal for this oxygen that I need to get rid of. Now the nice thing is that when you divide a constant by a constant, you get a new constant. And when you throw all that in here, this constant's going to blend in. So you don't even have to really think about all these constants. They're all just going to merge into one final constant. The real key point is that in here, I can substitute the O3 over the O2. Oh my God, really? Sorry, it's starting to freak out. And then, like I said, this blur of constants here will kind of combine with this constant here, and in the end, we'll just have a new constant. But notice now, oh yeah, go ahead.
To get that, would you multiply the constant on the bottom to the constant on the top? Or
Yeah,
how
but
would
we're not even going to worry about all that. We're just going to call it k again. You know what I mean? We're just going to let it all blur together.
Okay.
So in the end, it's just going to be k times k over k, you know, k. But notice that this now can be replaced by this, which is a reactant and a product. And when we're done, and I'm just about out of room here, we can write, and I'll put it in the corner here, that the final rate law is going to be equal to some constant, and then this O3 and this O3 are going to combine to make O3 squared, divided by O2. And so this becomes the rate law that matches this mechanism. Let's analyze it for a minute because it's actually quite interesting. This is why when you see actual experiments where we got like fractional orders or weird stuff like that, this even has a negative order if you think about it. When you see that, you're really telling yourself, oh, this reaction must be complex. It cannot be a simple elementary reaction. Elementary reactions are not going to have fractional orders, but complex reactions can. What is this telling us? It's telling us the more ozone there is, the faster this reaction happens. That makes sense. But why is it when there's a lot more oxygen, the reaction slows down? Isn't that weird? Like we usually think of increasing concentration makes the reaction go faster. This rate law is telling us that increasing the O2 slows the reaction down. But I think you can see from this mechanism why. If there's too much O2 in the way, it's going to kind of interfere with the ability of this step because notice that the O2 and the oxygens can combine with each other. So when there's lots of O2s around, this is going to mop this up before this can happen, right? In order for our second step to happen, the individual oxygen atom has to find another ozone. So when there's lots of O2 around, it gets in the way. And so it's kind of interesting. We can actually see the logic behind how the mechanism and the rate law connect to each other. But this substitution method is what you have to do if you end up with an intermediate in your original rate law from the slow step. Let me see the question. Sure, the intermediates can't stay there because they're not reactants or products. They're transient. They just appear and disappear right away. So you can't add more intermediate to affect the rate of reaction. You know what I'm saying? It's going to be a fast and short-lived species, so it's not really influencing the rate.
Are they always unstable?
Yes,
Okay.
relatively, right? There's unstable is a relative term. Some are going to be much less stable than others. Some will last literally billionths of a second. Some might last fractions of a second. So, but yeah, they're kind of stepping stones on the way from A to B. Let's look at one more example together, and then I'm going to kind of show you what's in the problem set and like what ones to maybe focus on if you want to practice this and get a hang of it. This is another one that's kind of kooky. And I already have the answer here, but for the sake of argument, let's see how they get this answer. And again, this is consistent with the idea that when there's a fractional order, there's probably a more complex mechanism than just a single collision. So like in this case, yeah, go ahead.
For this example, when it's 2Cl, would it cancel out with just Cl, or would it not be the same and you can't cancel those two out?
These cancel with both, right? Because there's two monatomic chlorines and there's two on the left side as well. So it's all gone.
Oh, okay.
And so that's an intermediate for sure, isn't it? I don't think there's a catalyst in this one, is there? No. By the way, just for the sake of argument, a catalyst can appear in a rate law. But here, intermediates would be the CL, and I believe the CCl3, because it's made and then used. And I think that's it, because our overall reaction will be chlorine plus, I think that's chloroform, makes carbon tetrachloride and hydrochloric acid. So this is the overall equation, right? So if we were doing the traditional method of rate laws, we would say something like this. Okay, here's my overall reaction. So my rate law is going to be some constant concentration of chlorine to the X, concentration of this thing to the Y. And then I would have experimental data to deduce it from. But we're not going to use experimental data. We're going to use this mechanism to figure it out. So let's see what happens. So we focus in on the rate determining slow step, and we write the original mechanism, the original rate law from there. So we start with rate equals some constant, an intermediate, which we're going to have to get rid of, and then this chloroform molecule, like that. And because this is an intermediate, we're going to have to do a substitution. What do we use for that? The fast equilibrium step, the one with the double arrow. Now I'm going to show you a shortcut. We know the K's are all going to mix together, so let's ignore the K's. For the substitution step, all I'm going to say is the chlorine part on this side is going to end up being equal to the chlorine squared on this side. Meaning that if we did what I showed you in the last slide, we would have had rate of forward equals K times this equals rate of reverse equals K times that. All I did is get rid of all the K's. And now it's a lot easier to see how this is going to go in. I need to substitute this, but right now I have the chlorine squared. If I square root both sides, that's like saying raise it to the half power, right? Now I have something I can substitute in, and I can see that my mechanism predicts that my rate law is going to look something like this with a fractional power here for the order. And then, wow, I'm really squeezing this in tight. And then this. And you can see that's the answer we get down here. So that's the essence of the lesson today, is just kind of that. How do we connect a sequence of steps called a reaction mechanism to a rate law? And how do we show that they're consistent or not? Any questions?
Wait, can you show what you did with the Cl2 equals the Cl squared?
Yeah, so what I did was I just kind of took away a lot of the fat that I wasn't going to use. So I would have written it as an equilibrium backwards and forwards. I would have said rate forward, and I'm looking at this first step here, equals some forward constant times this one to the first power. I would have said rate backwards, rate reverse, is equal to some other constant times the CL squared, right? But then I would have set these equal. I would have blended the constants. So what I did to make it easier is just said, well, in the end, all the constant stuff's just going to go away and blend together into one final constant. So then I just set this part equal to this part for the substitution. Because the rates are equal, right? When it's equilibrium.
Right. Is there a reason why you use the first one instead of?
Because of the equilibrium and because it also allows me to convert between an intermediate and an actual reactant or product.
Does it have to be at equilibrium?
That's what allows me to make the assumption to make the rates equal.
Oh, okay, I see that.
So if I could just jump over to the, let me find the right slide here. Okay, to the what the problem set looks like, just for FYI, so you know exactly how what we covered ties into this. And again, don't do them all. There's a lot. It's just meant to give you a sampling of the kinds of questions that are related to this. Um, oops, here we are. It's got to load. Come on, you can do it, computer. Put, 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 put. I feel like I'm driving a Yugo. So here it's asking you to write rate laws for elementary reactions. The key point is that you put it in terms of the reactants raised to their coefficients. That's all it's asking. So like the first one would be rate equals K times this thing to the first power. That's all. This is saying here's a mechanism, and then it's asking you what rate law would you expect? So here's where you take the slow step, write the rate law, and if there's no intermediates, you're good. If there's intermediates, you have to take the step of substitution. But here I'm pretty sure, since this is the slow step, it's as simple as rate equals K times this to the first power. And then it asks for things like what's the overall equation, what are the intermediates, etc. Here, there's some generic questions about these potential energy diagrams. So hopefully that will give you some clarity. Delta E here they're using instead of delta H. Don't let that bother you. When it asks here for molecularity, they're asking how many molecules are involved in this elementary collision. So like A has two molecules that have to collide, so it's bimolecular. B has just one molecule basically breaking open, so it's unimolecular. C has one molecular decomposing, unimolecular. That's all that's asking. Here, I think it's similar, if not, this is the same one I did in my example on the slide. So it's basically saying write the expected rate law, again, from the slow step, and then check if substitution is necessary for any intermediates. And so on and so forth. These questions kind of play around with different mechanisms and ask you to solve these kinds of problems. So hopefully that gives you enough of a grasp of this whole kind of section. And either you can rewatch the video or next time we meet, we can go over some of these again just to reinforce it. Any questions?
The one that had, if you could scroll up, I think it said 6. Number 6.
Oh, number 6, sure.
Yeah, that. Wait, why is it written like?
This triangle?
Yeah.
That's basically just a ring structure. So you can get different types of ring structures in chemical compounds, like where they connect back around on themselves and form like a loop.
Okay.
Mhm. Well, my friends, that's it for today. Thanks for sticking around all this time. And like I said, I'll post the video and you know where this is so you can come and look at it when you have time. But obviously focus on your equilibrium stuff for this weekend. And we'll see you next time. Have a great weekend.
Bye. Have a nice
Thank
weekend.
you.
Bye. Thank you.
Much. Have a good weekend.
You too.